Right now, somewhere over the Atlantic, a Boeing 777 is cruising at 35,000 feet. Inside that aircraft, 300 passengers, their luggage, a full galley of meals, and roughly 181,000 liters of jet fuel. But here's what almost none of those passengers know. That fuel isn't sitting in a tank somewhere in the belly of the plane. It isn't stored in a pressurized container in the cargo hold. It isn't locked away in some reinforced chamber near the tail. It's in the wings. Those long, tapered, constantly moving structures you can watch flexing from your window seat. The same wings bending in turbulence. The same wings that stretch and groan under load. That's where the fuel is. And when most people hear that for the first time, their immediate reaction is, why? The answer involves structural physics, thermodynamics, and a level of systems engineering that most people walking through an airport every day have no idea exists. Stay with me to the end. Because the final point, about what happens to the wings as the fuel runs out, is something most engineers don't think about until they study it specifically. And it flips everything you think you know about aircraft safety completely upside down. Let's start with the assumption most people make without even realizing they're making it. When passengers imagine aircraft fuel, they picture it the way they picture fuel in a car. A tank. Probably somewhere underneath. Sealed off. Out of the way. Safely separated from everything that matters. And that intuition makes perfect sense for ground vehicles. But aircraft aren't ground vehicles. They operate under an entirely different set of physical constraints. And one of the most important of those constraints is this. On an airplane, where you put weight is just as important as how much weight you carry. Weight placement determines structural stress. It determines aerodynamic balance. It determines fuel efficiency during the flight. And it determines safety margins across every phase of the journey from the moment the wheels leave the runway to the moment they touch down again. So when aerospace engineers in the early jet age sat down to figure out where to put the enormous quantities of fuel that long-range jet aircraft would require, they weren't just looking for empty space. Empty space is easy to find on an aircraft. They were looking for the position that would do the most engineering work simultaneously. The position that would solve the most problems at once. And they found it. Inside the wings. To understand why wing fuel storage is brilliant, you first need to understand the single most destructive force that acts on a commercial aircraft during every flight. It isn't turbulence. It isn't pressure differential. It isn't wind shear. It's lift. The same force keeping the plane in the air is simultaneously trying to destroy it. Here's what's actually happening. When an aircraft is flying, the wings generate lift along their entire span, from root to tip. That upward force is distributed across the whole wing, but it is greatest toward the tips, furthest from the fuselage. Meanwhile, the fuselage, the heavy body of the aircraft, full of passengers, cargo, engines, and systems, is pulling downward at the center. You now have enormous upward force at the wingtips and enormous downward force at the center. These two forces pulling in opposite directions across a rigid structure create what engineers call a bending moment. A rotational stress concentrated at the most critical structural point on the entire aircraft, the wing root, where the wing meets the body. On a fully loaded long-haul aircraft, this bending moment is extraordinary. The wingtips of a Boeing 787 can flex upward by more than 6 meters during flight. You can see it happen in real time if you watch the wingtip from a window seat. Those wings are not bending accidentally. They are engineered to bend. The alternative, a completely rigid wing, would require so much structural material that the aircraft would be too heavy to fly. But engineered flexibility means engineered stress. Every cycle of flex is fatigue loading on the material. Every landing, every turbulence event, every hour of cruise is adding to the accumulated stress on the wing root. This is the problem. Now here is how fuel solves it. When fuel is loaded into the wing tanks, its weight pushes downward along the wingspan. That downward force directly opposes the upward lift force. It counteracts the bending moment at the wing root. It reduces the stress on the most fatigue-sensitive structure on the aircraft. This is not a side benefit. This is not a happy coincidence. This is a primary engineering reason why the fuel is there. Every liter of jet fuel sitting in those wing tanks is doing two completely separate jobs. It is chemical energy stored for the engines. And it is a structural counterweight actively protecting the airframe. Think about the alternative. Suppose engineers moved all that fuel into the fuselage, a centrally located tank somewhere in the belly of the aircraft. The weight distribution would be completely different. The wings would no longer have that downward counterforce along their span. The bending moment at the wing root would increase substantially. To compensate, engineers would have to add structural reinforcement to the wing root. That reinforcement adds weight. That weight requires more lift. More lift requires more thrust. More thrust burns more fuel. A decision about where to store the fuel cascades through the entire design of the aircraft. Getting it wrong doesn't just create one problem, it creates 5. Getting it right, storing the fuel in the wings, doesn't just solve one problem. It solves several, simultaneously, with the same mass that was always going to be on the aircraft anyway. There's a second layer to this, and it involves a concept most people last encountered in a high school physics class: the moment of inertia. Here's the simplest way to think about it. Hold a heavy book out at arm's length and try to rotate it side to side. Now hold it close to your chest and do the same thing. The rotation close to your body is dramatically easier. The weight is the same. What changed is how far that weight is from the axis of rotation. Aircraft face this exact challenge in 3 dimensions. An aircraft pitches, rotates nose up and nose down, around its center of lift. Weight distributed far from that center, out along the wingspan, resists pitch movements. It gives the aircraft what engineers call pitch inertia. The plane wants to stay level. Small disturbances, a gust of wind, an air pocket, are dampened by that natural stability before the control surfaces even need to respond. Fuel in the wings provides that distributed stabilizing mass, and it does something even more specific than that. As a flight progresses and fuel burns, the aircraft gets lighter. Lighter aircraft need less lift. Less lift means less bending stress. But the fuel burn sequence is designed so that the tanks drain in a carefully managed order. Outer tanks first, inner tanks later, maintaining the ideal weight distribution and center of gravity at every phase of the flight. This means the aircraft's balance is being actively managed throughout the entire journey. Not by pilots manually adjusting loads. By the fuel system itself, by engineering that happens automatically, transparently, every hour of every flight. Here is something that surprises almost everyone who encounters it. Jet fuel has an enemy, and that enemy is warmth. Specifically, when jet fuel warms up, it evaporates. It produces vapor, and fuel vapor, not liquid fuel, is what ignites. Liquid fuel is relatively stable. Fuel vapor mixed with oxygen in a confined space is extremely dangerous. This creates a significant design challenge. Aircraft carry enormous quantities of flammable liquid through varying pressure and temperature environments. The goal is to keep that fuel as cool, as stable, and as vapor-suppressed as possible throughout the entire flight. Now think about where the alternatives would store it. Fuel in the fuselage belly sits near hydraulic systems generating heat, near avionics generating heat, near galleys and passenger cabins which are climate-controlled and maintained at comfortable temperatures. In the center of the aircraft, insulated from the outside environment. The wings are different. At cruising altitude, the air outside the aircraft is somewhere between -50 and -60 degrees Celsius. The metal skin of the wing is in direct contact with that environment. The wing structure itself acts as a continuous heat sink, conducting warmth away from the fuel and into the frigid air outside. Wing tanks are the coldest storage environment on the entire aircraft. The fuel inside them stays dense, stable, low vapor. This thermal management isn't incidental. It's a genuine safety advantage. And it comes entirely for free. No additional systems, no refrigeration, no energy cost, simply because of where the tanks are located. Here is the part that genuinely reorients how most people think about aircraft safety. Common sense says a full tank is riskier than an empty one. More fuel means more flammable material. More weight. More potential for something to go wrong. Common sense is wrong. Remember the bending moment problem. A wing full of fuel is a wing with a powerful counterforce acting against the lift-induced stress at the root. The wing is working hard, but the structural loads are balanced. Now think about a wing running on nearly empty tanks. The counterforce is gone. The lift is still there. The aircraft is still flying, still generating upward force across the entire span. But the downward mass that was offsetting it has been burned away. The bending moment at the wing root is now at its peak. The wing is experiencing maximum structural stress with minimum counterbalancing weight. This is why fuel management sequencing is so precisely engineered. The outer tanks, furthest from the fuselage, contributing least to the counterbalancing effect at the root, burn first. The inboard tanks, closest to the wing root, drain last. The system preserves the structural counterweight at the most critical location for as long as physically possible. Every drop of fuel burned on a commercial flight follows a sequence that was not chosen for convenience. It was chosen by stress analysts, aerodynamicists, and systems engineers working together to protect the aircraft structure from the first moment of lift to the last moment of touchdown. The fuel management computer isn't just keeping the engines fed, it's keeping the wings intact. The next time you find yourself in a window seat, watching that wing stretch out beside you, watch it flex. Watch it move. Watch the light catch the surface as it shifts slightly under load. Inside that structure, right now, there is fuel doing more than waiting to be burned. It's counteracting the bending stress that flight is constantly generating at the wing root. It's keeping the aircraft balanced and stable through every variation in thrust and airspeed. It's staying cold in the most naturally refrigerated compartment on the entire aircraft, suppressing vapor, maintaining stability. And it's draining in a sequence calculated to the liter to protect the structural integrity of the wing from the moment of takeoff until the wheels touch the ground. This is what great engineering actually looks like. Not a single clever trick. Not one good idea. A system where every design choice solves multiple problems at once. Where the decision about where to put the fuel simultaneously manages structural loads, aerodynamic balance, thermal safety, and fatigue life. Where the weight that was always going to be on the aircraft is positioned to do the maximum possible useful work at every moment of the flight. 500 tons of metal, fuel, and people, defying gravity every day. And the wings, those elegant, tapered, quietly brilliant structures, are a large part of why that keeps working.